Hello, welcome to CS571. So in today's lecture, we're going to talk about two things. The first half of today's lecture, we'll be first talking about advanced page tables. And this is the first half. And the second half of today's lecture, we're going to discuss some basics about memory virtualization, memory swapping. Okay, so in this particular video, we're going to first briefly go over what has been discussed in the previous lecture, paging and page tables. Okay. So what is page table and why there's a need for operating system to maintain page tables for different processes? Well, this is because, for whatever memory addresses that are visible or understandable, readable to the high-level user-level programs, user-level applications, or the developers. They are virtual addresses. They are logical addresses. They are not truly physical addresses that are understandable by the low-level hardware. So there's a need for the operating system to really provide this virtual address to physical memory address translation process. And this whole translation process is facilitated and supported by a special purpose in memory data structure, which is called a page table. Okay, and typically for each and every process within the operating system assigns a separate page table for each of the process. So if you take a look at this example shown this slide, as a toy example, it shows a 7-bit virtual address, okay? So the virtual address has 7 bits as shown over here. And first of all, how to decide the size of the page, the size of the virtual page or the size of the physical frame. And this is determined by the low bits, which is called the offset field. If you take a look at this example, this offset field has, the low bits part has 4 bits, right? So that means the size of the page is 2 to the power of 4, which is 16 bytes. So the page has 16 bytes in this case. And given that the length of the virtual address has 7 bits, and the high bits part has 7 minus 4, which is 3 bits, which is reserved for what is called virtual page number field. Okay, so this virtual page number field has 3 bits. Okay, so the job of the page table is to record such mapping, to map from the virtual page number fields to the physical frame number fields as part of the physical address. And this translation process is supported by what is called a page table data structure. And what particular data structure used to implement a page table? Well, as its simplest form, the operating system could use a linear array to implement the page table. Okay, so the index of the page table data structure is essentially what? Is essentially the virtual page number. And the operating system would just use the virtual page number to index into this linear array and to fetch the content, the value pointed to by that particular index. And this core value is what? The core value is the mapped result, is a translated result, which is the physical frame number. Okay, so after fetching the major content within a page table entry, which is essentially the physical frame number, the next step would be to construct the physical address. So how to construct the physical address is just simply concatenate the physical frame number field with the offset part, which is unchanged. Concatenate these two together to construct this so-called physical address. Okay. So in this slide, it shows a really simple page table example. Assume in this operating system, we are having two processes, P1 and P2. And both of these two different processes, they are maintaining exactly the same virtual address, virtual memory capacity. So the capacity of the virtual address space for both P1 and P2, they are spanning exactly 4 virtual pages as shown in this example. Okay, but why is that? So as you can see, within either P1's virtual address or P2's virtual address, they are having exactly the same set of virtual page numbers, right? Ranging from virtual page 0 all the way to virtual page number 3. But why is that there's no memory conflict or memory addressing collision? And this is because operating system sitting over here, right? It provides this so-called memory-based virtualization, which is essentially, this virtual address to physical address translation kind of thing. Okay, so operating system provide this memory virtualization so that from the perspective of a user process, in this case, either P1 or P2, they think they are having contiguous large enough virtual address space. But in fact, all these different virtual pages within their virtual address space gets mapped to like disaggregated, like physically disaggregated, non-contiguous physical frames within the physical DRAM, physical memory, as shown in this example. Okay, so this is exactly how the virtual pages gets mapped to the physical frames. So at the bottom of this slide, it shows the page table data structures, which are used to perform to record the mapping from the virtual address to the virtual page numbers to the physical frame numbers. If you take a look at P1's page table, so first of all, the index of this linear array is essentially what? It's essentially the virtual page number for process number 1, okay? So if you want to translate, if you want to get the mapping for a virtual page number 0, you just consult with this page table, and it automatically tells you physical frame number 2 gets mapped to virtual page number 0, as shown in this example as well. If you take a look at virtual page number 2 over here, which is the third value within this linear array, it gets translated into the physical frame number 0. Okay, so this is how exactly the third virtual page gets mapped to the very first physical frame. Okay. Okay, to zoom in to the page table entry. So this is how a page table entry looks like. So in this example, it shows the very first page table entry for P1's page table. Okay, so in this case, the size of the page table entry is from low bits, which is bit 0 all the way to bit 31, which has exactly 32 bits, right? Which means the size of each page table entry for P1's page table has 4 bytes. So to further look into the page table entry, the high bits, starting from bits number 12 all the way to the highest bit, which is bit 31. So all of these 20 high bits field, it has 20 bits. They are reserved for recording for storing the most important information within the page table entry, which is the physical frame number. Okay, so in this case, this physical frame number has exactly 20 bits. Okay, and the low bits field, starting from the lowest bit, the bit 0, to bit number 8, so a total of 9 bits. So all these 9 bits, they are reserved for storing the important bookkeeping information, basically metadata for the corresponding page, right? For example, this lowest bit is called P, which is a short of present, right? It indicates whether this particular physical frame is currently residing in physical memory or not. So in the next few recordings, we'll be talking about, a virtual memory swapping, and this part will be clear. Okay.